resonance. So in the last lesson, we talked about 4 possible situations for resonance to occur. A lone pair adjacent to a multiple bond, a positive charge adjacent to a multiple bond, a lone pair adjacent to a positive charge, and a radical adjacent to a multiple bond. We're going to do some examples and then also talk about major and minor resonance contributions. So we'll first start with this example here. Very similar to what we've already done before. And so we have a negative charge adjacent to a double bond, right? And so the lone pair, or the negative charge, essentially will drop down, forcing that to kick out onto the oxygen. So I'm going to draw the lone pairs that already existed, and then I'll go ahead and color code. So these were the lone pairs. They drop in. This will be the bond that drops up. And so when we draw the resonance structure, let me get rid of the grid. We're going to have the lone pair there, and we're going to have the double bond now between the carbon and the nitrogen, right? And so if we were to number, let's say we start with the nitrogen being 1, the carbon being 2, and the oxygen being 3, what happened is the lone pair on 1 dropped to form a bond between 1 and 2, and what was a bond between 2 and 3, or a double bond between 2 and 3, popped up onto oxygen number 3 in the form of a lone pair. And so again, I can number the other structure here too. Right. Now you notice the negative charge is now on the oxygen, and the nitrogen is now overall neutral. So I'm going to go ahead and erase this as not to confuse us, put it down here. But the nitrogen is overall neutral, and the overall charge of each molecule is still negative charge. We didn't increase or decrease the number of charges from one structure to the next. The structure, or excuse me, the charge is conserved across all the different resonance structures. And so we'll look at this and we will decide which of these 2 structures is major and which one is a minor resonance contributor. First, we're going to figure out which of these 2 structures have all octets met. And so if we look at structure 1 and we count the number of electrons on nitrogen, it's going to be 8 electrons. So nitrogen's good with an octet. This carbon has 2, 4, 6, 8 in the form of all bonds. So it's going to have 8 electrons as well, so its octet is full. And then the oxygen in the form of 2, 4, 6, and then that red double bond is going to be 8. So oxygen is also happy. So all the octets have been essentially satisfied. I'll erase this to get out of the way, but all the octets on the first structure have been satisfied. What about the second structure? Are the octets satisfied? Well, there's a lone pair here that I forgot to draw in, but nitrogen has a lone pair, and let's see here, I'm missing something. Oh, I added a bond there. So now that is the correct structure. Excuse me, it should have been a bond there in the first place. But now this is the correct structure. If you count, you have 2, 4, 6, and the blue bond makes 8. And so we have 8 on the nitrogen. So it's happy on this oxygen. It's happy with 2, 4, 6, and then the red lone pairs. So that's 8. And then the carbon is also 8. So both of these structures have met their octet. If one structure had not met the octet and the other had met the octet, then the one that meets the octet would be major. But in this case, both of them met the octet. The second thing that we have to look for is the negative charge on the most electronegative atom. And the third thing that we have to look for in deciding, also say how to decide which structure is major. Okay, and so the third thing we look for, if there's a positive charge, is the positive charge on the least electronegative atoms. Electronegative atoms want a negative charge, not a positive charge. So essentially, if we had the positive charge on the least electronegative atom, that would make it more major. So in this case, we don't have a positive charge. So 3 is moot. It's out. It doesn't matter. 1, both structures have the octets, and then 2, the negative charges on the most electronegative atom. Oxygen is more electronegative than nitrogen. So we'll say this is electronegativity. Oxygen is more electronegative than nitrogen. So we want the negative charge on the oxygen. I've mentioned this before. Think of the negative charge as if it's a dumbbell. The electronegative atom that is more electronegative is more capable of carrying the weight. And so oxygen, since it's more electronegative, is able to carry the weight of that negative charge better. And so which of these two structures have the negative charge on the more electronegative oxygen? It would be the structure on the right. So this would be the major resonance contributor. So that would be the major resonance contributor. So let's take a look at another example. Well, something very similar. Let's see here. And so we'll I'll go ahead and instead I'm going to keep these as implied carbons, implied CH3s, but I'll draw out the carbon on this one, just like I did here. So this was an implied CH3, that's an implied CH3. This is an implied CH3, and that's an implied CH3. I just drew the 1, 2, 3 atoms so that way we can get a better idea. And so this is actually going to be a positive charge, and we're going to do the resonance structure of this. So I will draw these lone pairs in blue, and we'll go ahead and drop those lone pairs down. And what's going to happen to the positive charge? We said 2 things happen whenever we have resonance. The first thing that happens is the double bond now becomes between the nitrogen and the carbon. So if I number the nitrogen 1, let's change my color, number the nitrogen 1 and the carbon 2, the lone pairs drop down between 1 and 2, forming this blue double bond. Now, the positive charge has to move. So the positive charge ends up, let's color that green. The positive charge ends up on the nitrogen, whereas it started on the carbon. So 2 things happened. First, the lone pairs dropped down to form a bond between 1 and 2, and then the positive charge had to move, and then now nitrogen carries the positive charge. And so this is going to be our resonance structure. If I wanted to work my way backwards, I could just move the arrow from the double bond back onto the nitrogen. And so what I would need to figure out is what is the major resonance contributor. So if I go and cover, let's see here, let me erase this and copy this on over. Okay, and let's go through here and figure out how we met our criteria. So does everything on these two atoms have an octet? Well, let's take a look at this nitrogen. So we have 2 in the form of these blue electrons, 4, 4, 6, 8. So the nitrogen has 8 electrons. The carbon has 2, 4, 6. In this case, it only has 6 electrons. That's what the positive charge is indicating. It indicates that the carbon does not have a full octet. So this is not quite satisfied. What about over here? Let's take a look at carbon. Carbon has now 2, 4, 6, and the blue bond would make 8. So in this structure, carbon is happy. What about nitrogen here? Nitrogen has 2, 4, 6, and then the blue, 8. So nitrogen is happy. So on the right side, we've met both of our octets. So the right structure will be major. So this will be the major resonance contributor because it has all its octets